Hi, I'm Meena Jagadeesan, and I'm going to be talking about joint work with Shuchi Chawla. So there's been tons of empirical evidence of skewed delivery in online advertising. So people from different gender and racial groups can see differing amounts of ads in sensitive categories like housing and employment. So what causes this unfairness? Well, the first source of unfairness is that the advertiser targeting is itself unfair. So this can be audited by looking at each advertiser's behavior in isolation. The second source of unfairness, which is more subtle, is that the platform's allocation algorithm can create unfairness even when the advertiser bids are fair. So even when each advertiser behaves fairly in isolation. So this source of unfairness has been empirically documented in sensitive categories like employment and housing. So the crux here is that unfairness can arise solely from the allocation algorithm. And eliminating this second source of unfairness is the goal of our work. So our contribution is a fairness framework that eliminates the unfairness introduced by the platform, and we build on our previous work. So we consider a simple stylized model for ad auctions in the online setting where we have a universe of users that arrive sequentially. When a user arrives, all K advertisers place bids on that user. The auction then allocates a single slot to that user, potentially randomizing over the K advertisers. Our contribution is ad auctions that do not introduce unfairness. So our ad auctions achieve constant fraction of social welfare compared to the unfair optimal and near optimal trade-offs between fairness and social welfare. So how do we define fairness? Well, we consider a fairness constraint expressed as a stability condition. So our starting point is individual fairness, which requires that similar users must obtain similar allocations. So since we're focusing on eliminating the unfairness introduced by the platform, we formalize fairness as a stability requirement. If two users have similar values from all advertisers, then they must receive similar allocations. So we formalize value stability as follows. So our value stability constraint is a function f that takes as input a multiplicative ratio between values and outputs the maximum allowable difference in allocation probabilities. So let's say we have two users and each has a value vector, and each advertiser has a value within a factor of alpha on the two users. Then we require that the L infinity difference between allocations must be at most f of alpha. So we measure closeness in values multiplicatively and closeness in allocations additively. So this value stability requirement captures that the auction itself does not introduce any further unfairness other than what might be present already in the advertiser's values. So now let's discuss the design of value stable allocation algorithms. So we start by describing why existing allocation algorithms are not value stable or have suboptimal social welfare guarantees. So let's start with the highest bid wins allocation rule. This allocates to the advertiser with highest value. So this has optimal social welfare, but unfortunately is not value stable since it can exaggerate small fluctuations in values. Consider proportional allocation now that allocates proportionally to the values. So we showed in our previous work this is value stable, but its social welfare approaches zero as the number of advertisers goes to infinity. So in this work, we design a family of allocation algorithms that are value stable and achieve a constant fraction of the social welfare regardless of the number of advertisers. So our solution is inverse proportional allocation. The core idea is to deduct proportionally to the inverse of the values. So we start by allocating an ad slot to all of the advertisers, then we deduct proportionally to the inverse of the values according to the blue arrows until the purple rectangles, which represent the allocation, sum to 1. So in our paper, we show that this process can be implemented efficiently. We also generalize to deducting proportionally to different functions of the values. So our main result is that inverse proportional allocation achieves value stability and a high social welfare. So in particular, a constant fraction of the social welfare compared to the unfair optimal, regardless of the number of advertisers. We also show that inverse proportional allocation achieves near optimal trade-offs between value stability and social welfare, regardless of the value stability constraint F. So in conclusion, we studied fairness in ad auctions and designed allocation algorithms that achieve near optimal trade-offs between fairness and social welfare. Thank you.